Hello! So you want to understand chemistry? That is awesome. To understand chemistry, you must understand the chemical reaction. Imagine you have some Lego bricks. You build a little house. Then you take the same bricks and build a spaceship. You haven't created or destroyed any bricks, just rearrange them. That is a chemical reaction. Substances called reactants are transformed into products. The atoms don't change. Bonds break and reform. The universe is a non-stop chemical reaction party. Everything around us is atoms rearranging. The key idea is change. Physical change. Ice melting into water. Molecules spread out. Chemical change. Burning wood. Wood plus oxygen. Ash, smoke, carbon dioxide. You can't get the wood back. Let's start with the most straightforward type of reaction. The one that's all about coming together. The synthesis reaction. The name itself gives you a big clue. To synthesize something is to make it, to combine parts to form a whole. In chemistry, a synthesis reaction is exactly that. Two or more simple substances combine to form a more complex product. A plus B yields C. It's like two people meeting at a party, hitting it off, and leaving together as a couple. It's a chemical union. A classic textbook example of a synthesis reaction is the formation of iron sulfide, yellow sulfur powder, gray iron filings. Mix them and add heat. Iron and sulfur atoms react, bonding to form iron 2 sulfide. Equation: 8Fe plus S8, 8Fs. You end up with a dark, brittle solid with new properties. Heat provides activation energy, like pushing a sled down a hill. That jolt lets atoms overcome reluctance and react. Outer electrons from iron are transferred to sulfur, creating ions. Iron becomes Fe2+, sulfur becomes S2. Opposite charges attract and lock atoms into a crystal lattice. This building up process is fundamental. Water, salts, rust, crystals all arise from synthesis. Hydrogen gas and oxygen with a spark combine explosively to form water. 2H2 plus O2, 2H2O. Synthesis reactions build complexity from simple parts. Now let's flip the script. If synthesis is about coming together, decomposition is all about breaking up. A decomposition reaction is the opposite of synthesis. One complex compound breaks down into two or more simpler substances. The general formula is A plus B. You start with one complex reactant, add energy, heat or electricity, and it splits apart. A great example, heating calcium carbonate, CaCO3, the main component of limestone and chalk. If you heat it strongly, calcination, it breaks down. It yields calcium oxide, quicklime, CaO, and carbon dioxide gas, CO2, CaCO3, Ko plus CO2. One solid becomes a different solid plus a gas. Heat pumps energy into the lattice, bonds snap and CO2 escapes, leaving Ko behind. Decomposition is vital in industry, for example, extracting metals. Aluminum is produced by electrolysis that breaks Al2O3 into elements. Hydrogen peroxide decomposes into water and oxygen. H2O2, H2O plus O2. Light speeds it up, which is why it's stored in dark bottles. The released oxygen makes it a useful antiseptic. From industry to medicine, breaking things down is as useful as building them up. Now we get to reactions with a bit more drama. Single replacement, also called single displacement, is where one element kicks another out of a compound and takes its place. General formula, A plus BC, AC plus B. A comes along and sees BC. If A is more reactive than B, it will boot B out and form AC, leaving B alone. It's a chemical competition. The more reactive element wins. Classic demo. Drop zinc metal into a solution of copper 2 sulfate, CuSO4. The zinc surface becomes coated with reddish-brown copper. The blue solution fades. Zinc is displacing copper. The reaction Zn plus CuSO4, ZnSO4 plus Q. Zinc has kicked copper out and taken its place. At the atomic level, zinc atoms give up electrons, Zn, Zn2+, which copper ions accept, Q2+, Q. Zinc dissolves, copper plates out. The reactivity series predicts whether a single replacement will happen. Elements higher can displace those below. Drop copper into zinc sulfate and nothing happens. Copper isn't reactive enough to kick zinc out. This principle is used to protect steel. Galvanizing coats iron with zinc. The more reactive zinc corrodes first, sacrificing itself to protect the iron. If single replacement is one dancer cutting in, double replacement is when two dancing couples swap partners at the same time. Two ionic compounds exchange partners to form two new compounds. General pattern: AB plus CD, AD plus CB. Positive ion A pairs with negative ion D, positive C with negative B. Example: mix potassium iodide, Ki, and lead-2 nitrate, Pb, NO3, 2. Both start as clear, colorless solutions. When mixed, a brilliant yellow solid instantly appears. Lead-2 iodide, PbI2. Full equation: 2KAQ plus Pb, NO3, 2AQ, PbI2S plus 2NaNO3, AQ. AQ means dissolved, S means solid. All four ions mingle. Pb2 plus finds I and forms an insoluble ionic solid, precipitate. K plus and NO3 remain dissolved. Double replacement is driven when a product is removed: precipitate, gas evolution, or formation of water, neutralization. These reactions are crucial for water purification and manufacturing pigments and many industrial processes. Now for the one we all know, combustion. This is, simply put, burning. A combustion reaction is a rapid reaction between a fuel and an oxidant, usually oxygen, producing heat and light. It's exothermic. It releases huge amounts of energy as heat and light. Take methane, main component of natural gas. With a spark, methane reacts with oxygen to form carbon dioxide and water. Balanced: CH4 plus 2, O2, CO2 plus 2, H2O. Heat and light are released. A spark breaks bonds and creates reactive fragments called free radicals. These radicals propagate a chain reaction, sustaining combustion. Carbon atoms form CO2. Hydrogen forms H2O. Product bonds are lower energy. The excess is released as heat and light. Combustion powers our stoves, cars, and power plants. But producing CO2 contributes to climate change. From internal combustion engines to power plants, controlled combustion converts chemical energy into mechanical and electrical energy. It kept us warm, cooked our food, forged tools. And now understanding combustion helps us mitigate its environmental impact. Understanding combustion is key to harnessing its power and reducing its costs to the planet. We now arrive at redox, a fundamental process underlying many reactions. Redox equals sign reduction plus oxidation. It's the transfer of electrons and changes in oxidation states. Oxidation equals sign loss of electrons. Mnemonic: oil. Oxidation is loss. Oxidized species increase in oxidation state. Reduction equals sign gain of electrons. Mnemonic: rig. Reduction is gain. Reduced species decrease in oxidation state. You can't have one without the other. Electron transfer is a paired process. Remember Zn plus QSO4, ZnSO4 plus Cu? It's a perfect redox example. Zn0 loses 2 electrons and becomes Zn2+. Zinc is oxidized. Q2+ gains those electrons and becomes Q0. Copper is reduced. Electrons move from Zn to Q. Many reactions are redox. Combustion: fuel oxidized to CO2, oxygen reduced to H2O, rusting, iron oxidized, batteries, metabolism. Redox underlies batteries that power devices, cellular respiration that produces ATP, and corrosion that degrades metals. At its heart, redox is the movement of electrons, the currency of chemical energy. That movement explains energy changes in many reactions. It's easy to think reactions only happen in labs, but they're everywhere, all the time. Your body is a walking chemical reaction factory. Digestion is a series of decomposition reactions. Enzymes break large molecules into absorbable pieces. Carbohydrates become sugars, proteins become amino acids. These smaller molecules are absorbed for energy. Cellular respiration is essentially slow, controlled combustion. Glucose reacts with oxygen to produce ATP, the energy currency of cells. In cooking, baking soda decomposes to make CO2 that leavens cakes. Heat triggers the Maillard reaction that browns and flavors food. Soap molecules form micelles that trap grease, allowing oil and water to mix and be rinsed away. From rusting cars to ripening fruit, everyday life is full of chemical transformations. Double replacements help purify water. Synthesis yields pigments and new materials used in industry. Chemistry gives us life-saving medicines, advanced plastics, and fertilizers that increase crop yields. It also helps clean the environment by neutralizing pollutants and treating waste. Understanding reactions helps us manipulate the world, from powering devices to producing food. Chemistry is the science of change, and reactions are how that change happens. We toured synthesis, decomposition, single and double replacement, combustion and redox, the basic moves of chemistry. These reactions help build materials, make medicines, grow food, and power modern life. From stars forging elements to the primordial chemistry that led to life, chemical change is the story of everything. We are made of and sustained by these processes. Thanks for watching. Keep exploring chemistry.